Coulomb's law. We know that there are two kinds of charges, namely positive and negative charges. The charge on an electron is assumed to be negative and charge on proton is positive. Moreover, we also learned like charges repel each other and unlike charge attract each other. Now we investigate the quantitative nature of these forces. The first measurement of the force between electric charge was made in 1874 AD by Charles Coulomb, a French military engineer. On the basis of these measurements, he deduced a law known as Coulomb's law. It states that the force between 2 point charges is directly proportional to the product of their magnitude of charge and inversely proportional to the square of distance between them. It is mathematically expressed as F directly proportional to Q1, Q2 and inversely to R square, or F is equal to K Q1 Q2 over R square, where F is the magnitude of the mutual force that acts on each of the 2 point charges Q1, Q2 and R is the distance between them. The force F always acts along the line joining the 2 point charges. K is the constant of proportionality. Its value depends upon the nature of medium between the two charges and system of unit in which F, Q and R are measured. If the medium between the 2 point charges is free space and the system of unit is SI, then K is represented as K is equal to 1 over 4 pi epsilon, where epsilon is an electric constant known as permittivity of free space. In SI units, its value is 8.85 multiply 10 into raised power minus 12 nm square c minus square. Substituting the value of epsilon, the constant K is equal to 1 over 4 pi epsilon is equal to 9 multiplied by 10 to raise power 9 nm square c minus square. Thus, Coulomb's force in free space is F is equal to 1 over 4 pi epsilon naught Q1 Q2 over R square. As stated earlier, Coulomb's force is mutual force. It means that if Q1 exerts a force on Q2, then Q2 also exerts an equal and opposite force on Q1. If we denote the force exerted on Q2 by Q1 as F2 and that on charge Q1 due to Q2 as F12, then F12 is equal to minus F21. The magnitude of both these two forces is the same and is given by the equation that we early studied. F is equal to 1 over 4 pi epsilon Q1 Q2 over R square. To represent the direction of these forces, we introduce unit vector. If unit vector R21 is the unit vector directed from Q1 to Q2 and R unit vector 12 is the unit vector directed from Q2 to Q1, then F21 is equal to 1 over 4 pi epsilon Q1 Q2 over R square and unit vector 21, and then second F12 is equal to 1 over 4 pi epsilon Q1 Q2 over R square, then R unit vector 1 2. You can see here differences. In first equation R12 and second equation showing that are 2-1. The force 2-1 and force 1-2, it can be seen that R21 is equal to minus R12. So we can say that F21 is equal to minus F12. The sign of the charge in equation determine whether the forces are attractive or repulsive. We shall now consider the effect of medium between the two charges upon the Coulombs force. If the medium is an insulator, it is usually referred as dielectric. It has been found that the presence of a dielectric always reduces the electrostatic force as compared with that in free space by a certain factor, which is a constant for the given dielectric. This constant is known as relative permittivity and is represented by epsilon r. The value of relative permittivity of different dielectrics we can find in Google. Okay, thus the Coulombs force in a medium of relative permittivity epsilon r is given by F is equal to 1 over 4 pi epsilon, and then epsilon r also multiplied by this, and multiply again q1 q2 r square. It can be seen in the epsilon r for air is 1.0006. This value is so close to 1 that with negligible error. Okay, this gives the electric force in air. Thanks for watching.